let us discuss this theorem. Okay, so in this theorem we have a matrix space xd and A is subset of X. Here we have to prove two things. Let us start to prove first part. What we have to prove? A bar is a closed set. I will write to prove that A bar is a closed set. So how to prove that any set is closed? We have one option, that is we can prove that its complement is open, and second option, if the set contains all its limit points, then also we can declare it is a closed set. So a bar means closure of A. We have to prove that it is a closed set. So I am going to use second thing. That means I am going to prove that this set contains all its limit points. So that's why we can declare it is a closed set. Okay. So I will simply mention that is to prove that A bar contains all its limit points. Okay, we have to prove that it contains all its limit points. I am taking one arbitrary limit point of A bar and I will prove that it is in A bar. Let X belongs to A bar be any, I should mention, let X be any limit point of A bar. So I have taken one arbitrary limit point of A bar. We have to prove that it is in A bar. So then we can declare A bar contains all its limit points. Okay. So you are familiar with the definition of limit point. Definition of limit point is BXR minus singleton X intersection A bar is not equal to phi. This is true for all r greater than 0. So you know this, you are familiar with this definition of limit point, but see, there is one more definition of limit point, and that second definition I am going to use it. See, maybe you are thinking what is the second definition? So the second definition says, I will show you. So by second definition, therefore, for given epsilon greater than 0, there exists y belongs to A bar, okay, where y is not equal to x, such that d of xy less than epsilon. This is statement number 1. Okay, so when we say it is a limit point, that means it is very close to that set, then we can say it is a limit point. Getting? So here this is a limit point. So I will show you here. I will try to show you in a form of diagram. Suppose this is any set A bar. Okay, suppose this is A bar. So when we say X is a limit point of A bar, if you draw any open ball around X, it contains some point of A bar other than X. So the same thing I have written in a different way. What I have written here, X is a limit point of A bar. So that's why it is possible to find some Y belongs to A bar. Getting? It is possible to find some Y belongs to A bar other than X, such that distance between X and Y is less than epsilon. Getting? So then we can, this is also another definition of limit point. So using epsilon definition of limit point, I am going to prove it. Okay, so this thing we have, again there is one adjustment I am going to do. So that adjustment is, instead of epsilon I am taking epsilon by 2. Okay, see, we have one thing, that is y belongs to A bar. See, y belongs to A bar, that means y belongs to A bar means what? A union A dash. Agree with me? That means y belongs to A, union means or, y belongs to A dash. That means y is a limit point of A. That means again I can use such type of definition there. Y is a limit point of A. So therefore here we have some space, let us use it. So therefore for given epsilon, but see already one epsilon we have taken here, so I will say for above epsilon. For above epsilon greater than 0, there exists some z belongs to A, since this is a limit point of A, I'm saying, huh? So there is one point z belongs to A such that d of yz less than epsilon. Again, an adjustment I'm going to do, that is epsilon by 2. Okay, so this is statement number 2. So maybe you are thinking, why I have not written y is not equal to z? Because here we have two options, either y is in A or y is a limit point of A dash. Limit point of A. So therefore, I skip that step, getting y is not equal to z. That step I skipped there, and directly I wrote this one. Okay, so I think you have understood what I'm going to do after this. So I'm going to combine. Here is epsilon by 2. There is also epsilon by 2. So I'm going to combine it, but using triangle inequality I'm going to write. There is no more space to write. Make a screenshot of it, then we will go further. So by triangle inequality we can write d of xz is less than or equal to d of xy plus d of yz. See, in star already in statement 1 and 2 we have already said this is less than epsilon by 2. This is also less than epsilon by 2. So I will mention from 1 and 2. Getting from 1 and 2. So this is equal to epsilon. So finally we proved, therefore, what we have got here, d of xz less than epsilon, where z belongs to A. Where z belongs to A. So I am using the same definition in a reverse way. Getting now? So this is a definition of limit point again. So therefore x belongs to A dash. So therefore this is a definition of limit point. So x is a limit point of A. So therefore x belongs to A dash. Right? But see, same thing we can write, x belongs to A union A dash. See, x lies in A dash. So therefore it lies in union also. So this is nothing but A bar. So therefore x belongs to A bar. Actually, x is a limit point of A bar, and finally we proved x belongs to A bar. So that means A bar contains all its limit points. So let me write that thing here. Therefore, A bar contains all its limit points. Okay. So this is one of the definition of closed sets. So yeah, you have to keep in your mind, when we say set is closed, if its complement is open, no doubt. Getting? But there is one more definition which we have proved in our previous video. That is, if any set contains all its limit points, then also we can declare it is a closed set. So using that second definition, we have proved it. A bar is a closed set. Therefore, A bar is a closed set. Okay. So in this way we proved the first part of it. After that we will try to prove the second part also, but make a screenshot of it, then we will go further. See, in second part there is if and only statement. That means we have to assume one part. After that we will prove second part, and in a reverse way also we have to do. So let us assume first A is closed set. Assume that A is a closed set. Getting? So see, set is closed. That means we have two options. Either we can say its complement is open, or you can write it contains all its limit points. So the second thing I am going to consider. So therefore, A contains all its limit points. Okay. So symbolically we can write the same thing in this way. Therefore, A dash subset of A. Right. So I will take union A on both sides. So therefore we will have A union A dash subset of A union A. Are you familiar with this? A union A dash is nothing but closure of A bar. So therefore A bar subset of A union A is A. So very important thing we have got. I will call it as equation or statement star. Okay. Let us go further. See, we know that what we know that A bar is equal to A union A dash. What is definition of A bar? A union A dash. So that means A bar is a union of A and A dash. So obviously each of them is subset of A bar. So therefore we can write, so implies A subset of A bar. So this is, I will say, double star. See, tell me, if I combine star and double star, what can we write? From star and double star, getting A subset of B, B subset of A, therefore both of them are equal. So from both of them we can say A is equal to A bar. So in this way we proved half part of sub question B. After that we will go for a remaining part. So make a screenshot of it, then we will go further. See, conversely we assume A is equal to A bar and we have to prove that A is closed set. Okay, so I have already assumed. So implies A is equal to, you know that A bar means A union A dash. So we are taking union of two sets, then also we are getting one of these two sets. So that means the second set is 100% subset of first set. So here also A union A dash is equal to A, that means A dash is subset of A. So therefore A dash is subset of A. It means A contains all its limit points. So therefore A contains all its limit points. Okay, so A contains all its limit points. So this is definition of closed set. So therefore A is closed. So as I told you earlier, A is closed when its complement is open, or in another way we can say A is closed if it contains all its limit points. So I proved A contains all its limit points. So that's why we can declare A is a closed set. So in this way we have completed this example. Make a screenshot of it. After that we will stop. Thank you. Bye bye.